Good afternoon. My name is Alberto Cabri, and today I'm going to present the result of my PhD research in the last 3 years. Okay, the topic we're going to see is a quantum-inspired approach for early classification of time series. So we will go through the motivation, the proposed models, some validation techniques that I applied to test if the proposition was working properly, and a real-world application, and we will draw some conclusions about the application of this new method. So the main motivation is that we have a huge amount of data which is now collected from IoT devices, from a lot of different sources, and definitely they pose new challenges to researchers, mostly because they are time indexed data streams and require continuous monitoring. And most cases, we also need to take timely decisions because depending on the behavior of the sources, we will need to take corrective actions or we will do some other actions. Um, Time indexed events are in some way related to the preceding events. So they're related neighbors, and automatic classification becomes now a key task because it is better if we can take decisions according to the evolution of the data that we have against time. So the approach that I'm proposing now is an application of the fundamental principles of quantum computing to the time series classification in real time. So, as a general definition, we can consider that another list of data related by some rule is a sequence. And in our case, we define that we call it as a session because we want to divide sequences depending on where they come from or what are the reasons why we are collecting those and group them according to a certain logic. So we have a time-dependent order, and so we say that this is becomes a temporal sequence or a time series. For the time series, we can assign one or more class label, and we can do this in two different flavors. In one case, we can do offline classification, and in this case, we need to have a whole sequence. The sequence is complete, the sequence is finished, and we can just analyze the sequence as a whole. Whereas when we do online classification, we are doing on the fly or online classification or real-time classification. In this case, we are targeting what we call early classification because the aim is to have a decision in the shortest possible time with the highest possible accuracy. So, one of the possible approaches to this activities, to this task, is the sequential probability ratio test defined by Wald in 1945. And it is a sequential test for statistical hypothesis. It's suitable for binary sequential problems with independent identically distributed events. And in our flavor, in our definition, we have three possible decisions, which is we can accept the null hypothesis, we can reject the null hypothesis, or we can delay the decision and consider additional event if any. So the test continues until we can select either 1.1 or 0.2, and so take a decision. So the number of observations required to make a decision cannot be established a priori, but can be estimated by means of some considerations about the possible types of error. We have an error of the first kind, which is rejected null hypothesis when it is true, or we can have, and we call it alpha, or we can have an error of the second kind, which is accept the null hypothesis when another one is true. And this we call beta. There are optimal properties because in this algorithm the errors can be upper bounded. So we decide a maximum value for acceptable for the error, and we can state what alpha from alpha and beta we can define the parameters that we need to apply, the thresholds that we need to apply in order to have this acceptable error. And we don't need any probability distribution to execute the test. We simply analyze the samples. So, formal definition. Okay, so if the decision is belongs to 0, 1, or none, and are all mutually exclusive, we can consider a sequence X given by some xi events from x1 to xk. So our sequence is X, capital X, and contains k events. Then there are characterized by an unobservable class y in 0, 1. So we consider the joint conditional probability P of x1, xk, given that y is C, is class C, and we define the ratio given by this Rk, by this equation, and given this ratio, we can then take a decision by first selecting the optimal values for A and B for the threshold, the decision thresholds that come from these two equation 1 minus beta divided by alpha, or beta divided by 1 minus alpha, that are related, as you see, from the error of the first and second kind. So we can decide, take a decision that is 1 if Rk is greater than I, it's 0 if Rk is lower than B, and none if it is in between. So our last decision, if our last decision is none, decision is left undecided. We don't want to take any decision because this means that there is not enough information to take a reliable decision on this sequence. And we will see that this is interesting because in some techniques people generally tend to classify with a different method, but it's a deviation in the task because our task is to decide online. And if we deal with the whole sequence because the stream has finished, what we have is that it's no longer the same problem. It's no longer the same problem because if this was, let's say, a dangerous attack to a website, and we want to intercept this attack by means of analyzing the stream, the attack is over. So it's no use to take any decision in this case. So we want to intervene on time, online. My proposal, which is quantum inspired, is based on some quantum computing principles, and it's mainly based on the two main properties that are superposition and entanglement. So superposition means that you can add together any valid quantum states to obtain another valid state and vice versa. And entanglement means that the state of two or more particles can be so tied together that it cannot be described independently of the others. And this also happens when they are far away from each other, because you know that entanglement can work also with a lot of miles in distance from the two particles. Mm, so the qubit is, in this case, the quantum analog of a classical bit, but it contains not only 0 and 1, but a lot of blended informations that stay in between 0 and 1. For this new technique, we use the quantum notation, so we use the cat notation, and so we define two column vectors that represent the basic state cat 0 and cat 1, and so that we can express a pure qubit state by adding together those basic states 0 and 1, cat 0 and cat 1, with two probability amplitudes that we call now alpha and beta, and are such that the squared value of alpha and plus the squared value of beta add up to 1. And so in this case, their square values are probabilities, and the alpha and beta are just called probability amplitudes. So we use the tensor product operator that we can indicate with this x in the circle, and this computes a composite state for two or more qubits. So we can define this cat 011 as the composition, the entanglement of cat 0, cat 1, and cat 1. And we can consider a state entangled if we cannot decompose it in its fundamental parts. As you can see, it is not possible to get back from 001 and decide what are their probability amplitudes, because it's impossible to switch back to the composition. So in this case, we can define cat the status psi, the cat psi, as 1 over square root of 2, which is necessary to have equal superposition, which is the cat state. You remember the experiment of Schrödinger, the cat of Schrödinger. And you have that cat 00 plus cat 11 define in equal superposition this new state, this new state psi. So what are the differences in this case from a real quantum system? The differences are basically that measurement process, which is the way we extract information from the quantum system, is kind of destructive operation in the real system, because it alters the state of the system, and because the system turns into the pure state that represents the outcome of the measurement. And we also have that the probability pk of the system is the probability that the system stays in the state k can be measured from each system. And another property is that when we have only two basis states, known P0 as the probability of status 0, then P1 is complementary, is 1 minus P0. This is in a real quantum system. For n classes, so we can expand this approach in order to have a multi-class classifier, a multinomial classifier, and we define the vector, the basic states vectors as column vectors that contains n items, n elements, for cat 0 to cat n minus 1, and we define the pure bit qubit state as the superposition of the n basic states, as we said before, as we did before, in the two states, with the two states only. So we have that psi is defined as alpha 0 times cat 0 plus alpha 1 cat times cat 1, and so on, where each alpha I squared represented the probability of state I, and the sum of all probabilities are up to 1. So we should make some assumptions, because at each time step t we define that fi of xt with I given in 0 and minus 1 is the class conditional probability of event xt for the sessions that we are going to classify. So the class probabilities estimates should be available. This is one of the assumptions that we need to do. And all observations in the sessions should be time dependent. In this case, we can define all the alpha I comma t as the square root of this probability, the probability fi of xt. So each event has its own probability of belonging to a certain class, and we define all the coefficients as the relevant the probabilities related to each of the classes. Okay, so I are the classes, t is the time, and this is a new event in time. So at each new event in the sequence of length s, so we have s events for each sequence, we can create an s-qubit entangled state that contains all the estimates for all of the classes for all of the sequence events, which defines psi as for a class for class I is psi I as alpha with the cat of all eyes. So the number, the length of this entanglement depends on the number of events in the sequence. And so you see here that we can combine those events for each of the classes. So in this case, in the example, we have how to build, we can see how to build it for class 0. So then we combine all those equations into the one that represents the stream of S events for all possible classes. And you see that we have this superposition. So when we measure now at each time step, we measure the state psi, we obtain the probabilities for each of the classes, each of the possible classes in 0 and -1. And those are normalized class probabilities. So we can take a decision, I, if the probability of class I at time t is greater than a certain threshold C, which is task dependent, or none if otherwise. And again, like exactly like in SPRT, if we end up with a sequence that has not been decided when it finishes, well, we cannot take any decision. We leave it as undecided. Also, this allows to compare the two methods because we have exactly the same outcome. So, to validate this approach, we want to have a sequence of probability estimates. And so we associate each event in a session to a vector of class probabilities. And here you have an example of how we generate the test set, the validation set for the approach. So we have session 0, which contains 2 events, and for each of the events, we have the label, which means target, and the probability estimate that we build with a certain algorithm that are kind of biased for the target class. And the same we do for class 1. We have 3 events, 3 or more events, and again the target is class 1, and we see that it's slightly balanced, slightly biased for class 1 again. The way we create that is by simply defining a probability for random probability, random value between 0 and 1 for the target class, and then divide the remaining probability randomly for the rest of the classes, and then we add up again to the target class. To have this small bias, which is not necessarily greater than the other one in the final output, the final outcome for each row, but as a whole, in the sequence, we tend to have a slightly biased probability for the target class. Well, we have created a test with 3 data sets, 2 to 4 classes with the 10,000 sessions with up to 100 events in length. And this is one problem that we have with this approach is that for the current implementation, when you use a tensor product and you combine a lot of events with many classes, the mechanism tends to explode in memory, and so I implemented kind of people mechanism in which we see only a short part of the time series, only the last n samples with n that generally can be from 4 to 8, which is a good option. And if we consider only the last 8 values, we can see that still we get the same results that we have without giving up too much in accuracy or on other metrics. So we also used the Pareto frontier to optimize the contrasting goals, because we have contrasting goals. We have that we want to maximize accuracy, but we want to reduce the number of undecided sessions. And again, we want to reduce the decision sequence length, because we want to take the decisions as soon as possible, and leaving the accuracy on the top value. So we made some grid search approach to with the confidence levels coming from 0.55 to 0.998 with a constant PIP value of 4, and we left the undecided sessions in the matrix because it's a penalizing factor. So here we see that what are the results. So we can see that in the validation data set, we can minimize the longest decision sequence. LDS is the longest decision sequence. And if our goal is this, with the true possible threshold that represent the optimal values on the Pareto frontier, is that 0.55 gives more or less 2,000 errors, and we have no unclassified sessions, but the accuracy is then 82.84% with the longest decision sequence up to 3. We can, on the contrary, minimize the LDS also by having the threshold at 0.998, which gives us 0 error, but a small number of unclassified sessions, because remember, this is 251 out of 10,000. So our accuracy is 97.5% with some decision sequence that may last up to 27 samples, so 27 events. If we want to minimize the number of unclassified sessions and we consider this as a goal, we can see that, again, we can minimize the number of unclassified sessions by having 0.8 as a threshold and 87%, 87.5 with a longer decision sequence of 5. And again, the same threshold is good, because it's the same threshold that minimizes, it's good for both target, for both goals. We can minimize the number of errors, minimize the number of unclassified sessions, just obtaining the same exact result. So it's clear that we could select this option, this classification threshold, 0.998, because we can see that at a deeper analysis we can have the 70% of sessions classified within the 5th event, and the 90% of sessions classified within the 8th event. Even if some can go up to 27 events, the greatest majority of sessions gets classified within the 8th event. So if we use the same approach, this is on multiple classes. So we consider a fixed threshold on multiple classes. We can see that we can have for 2, 3, and 4, we can have 2 errors or even 0 errors, and get up to 98.89% in accuracy with the longest decision threshold, which is 11, or again less than 27. What is important here that I also computed the average decision sequence by weighting how many samples are decided at each time step are correctly, well, yes, are decided, not correctly, decided correctly or wrong, but decided. And we end up to have that the average decision sequence is still less than 5 for all the possible approaches at 0.995. So a good application that we tested is bot detection. Bot detection is cybersecurity application that we tried to tackle with this new approach. And web robots are just pieces of software that perform automatic actions on network computers, such as crawling, indexing, and are also for maintenance purposes. But the main problem is that more than half the traffic of a website is due to bots. And even if there are some ethical bots, lots of web robots are malicious. And so they can perform fraudulent activities and can also operate from different IP addresses, try to mimic human beings' behavior. So it's kind of a dangerous software for a website. Also because they do not respect the rules that are generally described into the robots.txt file, which is exactly available on a website exactly for this reason, to control the behavior of robots, of ethical robots. So, what we wanted to do is that we want to analyze the website usage logs and be able to distinguish the legitimate human crawlers from bots by using computational intelligence. So, we wanted to take it's a clear problem of early decision because we want to be able to identify as soon as possible the web robots and block it if necessary. So we have two possible types of problems in literature. One is offline recognition. So we have, as I said, we have a complete web session, and we want to label it as bot or non-bot. And in this case, it's no real advantage because we have uh, we have a session that has been already done, has been already completed. So if any damage has been applied to the web server, it's done. We cannot do anything else. And the most interesting task for me is online recognition because we want to detect bots as soon as possible before the session ends. So we consider again the requests that are time-ordered sequences of descriptive features, and we analyze the HTTP request logs. We have a correlation definitely between the two subsequent events because if you think about how you generally surf the web, you don't download an image without getting into the HTML page first. So there's a relationship in the way you access resources if you are a human. Whereas bots can access only images or can access only other type of resources without even accessing the web page. So we want to take a decision in the shortest decision time because we want to minimize the negative impact of bots, as I said before. And again, we need to take into account that HTTP is a stateless protocol. So we must have a way to define what a session is, because a session is not defined as a TCP/IP connection. If you have a TCP/IP connection, you have a connection which is stable until you close it, and it's clear that all the packets that flow into these connections are the session. In this case, a session can be tricky to define, and so we take what in literature is the common definition of a session. A session is a time-ordered stream of HTTP requests and that are coming from the same IP address or that end from the same user agent string, and for where the delta t between the two subsequent requests is less than 30 minutes. This is the feature list. Feature list that you can see where what we extracted from the request log, and we started from these 10 feature columns, and by some pre-processing, by mapping true false to 0 1, by mapping the HTTP code to 1-hot or the HTTP method to 1-hot encoding, so we end up with 25 features. And so we feed the classifier with 25 input features. So what are the challenges here? The challenges are that the sessions have an unknown variable length and that bots are smart enough to change their navigation style. So we have no a priori information on user agent string that are able to identify bots because if they want to hide themselves, they specify also fake user agent strings. And so we want to take, as I said many times already, a reliable decision as you go. So we have a problem of sequential processing of correlated and time-dependent requests. So each individual event needs to be estimated in its probability. So we first perform an individual event classification by a multi-layer perceptron with k-fold cross-validation, and we obtain an accuracy of 95% only on the individual events, which somehow confirm that there is a kind of structure inside the behavior mm, of our of bots against humans, because accuracy can be done also without considering the sequential structure. But a sequential structure is present because it's confirmed also by some heuristic tests and from literature. So we implement a sequential decision criterion with the reject options at the event level, as I said. So we decide that 1 is the output if the crawler is a bot, and we do not sample any other observation. 0 if the crawler is human, or none if we want to skip to another event and consider another event in the session. So our architecture is based on a two-stage model, both for SPRT and QMC, because we wanted to compare the two methods and to see how they relate them to themselves and which one is better. In this case, also because SPRT is a pretty stable method. Well, it's defined many years ago and well defined in terms of mathematics. So QMC is new, and I want to check against SPRT. Scikit-learn MLP classifier is followed by a sequential decision model, which can be either SPRT or QMC. And here is the breakdown of the multi-layer perceptron, which is two hidden layers of 50 units, one input layer of 25 input features, and two output layer with softmax in order to have something which can be related to a probability. For cost function, we use cross entropy, and for hidden layer activation function, we use a ReLU with k-fold cross validation with the 10 sampled splits. So what we have here is that, again, a formal definition of SPRT is assuming that probabilities are provided by MLP, and we relax the constraint because, as I said before, SPRT should work with IID events. In this case, we consider them as independent, even if they are not, because we know that there is a relationship between subsequent events in time series in this kind of time series for navigation. So the ratio is defined, as you can see in the equation, and we transform it into a logarithmic form to avoid numerical issues, because sometimes with small values we can face some numerical issues. So we set the error rates according to the world theory, and we define two thresholds, C0 and C1, for humans and bots respectively. So the classifier outputs according to this rule. Decision is taken at each time step k, and if decision n is none at the end of the sessions, the session is classified as undecided and considered an error, because we were not able to take a decision. Our task is take a decision, so if we don't take a decision, it's an error. And for QMC, it's pretty much the same approach. We consider the probabilities f1 and f0 of the two classes, one for bots and 0 for humans at each time, each new event xk, and we obtain the probabilities by the multilayer perceptron as well. And in this case, we have that all observations in the session are exactly time dependent. And so we can define the probability amplitudes as the square root of the two individual probabilities estimated by defining alpha k and beta k. And so we can combine for each subsequence, each sequence of S events, we can define an S-qubit entangled states, two S-qubit entangled states, psi0 and psi1, created with this equation, by this equation, and then combine those in equal superposition, obtaining one unique state that represents the whole system, and so the whole sequences. So we define two thresholds as in SPRT with a different level of confidence about the decision, because we might want to take a decision if the confidence levels are different for both for bots or humans, and again we leave that as undecided if at the end of the sequence we could not take any relevant decision. You see that we only measure here the probability of state of the basic state 0, because it's only two states, so they are complementary, and so we decided that we consider the two probability. If the probability of state 0 is lower than C1, it is a bot. If it is greater than C0, it's a human. Okay. So we only measure one, and in this case we must say that the measurement is not destructive, because we can measure, if we have a multinomial situation, we can measure the state of all classes because it's performed via a software approach. So we cannot we can measure the state without being destructive. So the experimental part of this technique was set up on a dataset provided by a Polish e-commerce website with over 13,000 sessions and more than about 1.4 million HTTP requests. And we had a multilayer perceptron as defined before at the first stage. We use the training validation split with the 34 or 30-70%. So we use the 30% for training and 70% for validation, which is pretty much unbalanced because unbalanced in favor of validation. So we have you can see that we have a very small training set. And the unknown probabilistic model of data is estimated by multilayer perceptron. Grid search is more reliable in this case than Wald's theory for threshold selection for the quantum approach. So we applied the Pareto optimal threshold for decision speed and accuracy by selecting for the SPRT the best options that are 0.10 and 0.85, and for the quantum approach 0.25, 0.95. Sorry. So here you have the results. The results are that for at the SPRT best thresholds, you see that QMC have a greater value of accuracy with the 15 unclassified and the smaller error. So we see that we have that K90 is the step at which we classify the 90% of the sessions. And you can see here that we can achieve with SPRT of 90% or more than 90% of decisions at the first step, whereas in the quantum inspired approach we use two, we need at least two, but still we are going forward and we have a higher classification accuracy, and the decision sequence is not too much not too different. Also consider that when a bot or a human performs a request on a web page, in the first access you can download more than, you can perform more than 5 requests, because every resource has been requested with the same from starting maybe from the first page. So it's 5 requests is still the first access to the website, in most cases. And for the result of the quantum inspired approach, again, you can see that there's even a greater difference in the classification accuracy, because in the QMC Basters thresholds, we obtain 95% with the even smaller, much smaller number of errors. And even if we have some more unclassified session, we have a much smaller error, and more or less the rest of the parameters of the yes, the values are the same, the metrics are the same. So we have K90, which is 2 or 1, and the longer decision sequence is again less than 7. And here you can see the two plots of of what happens in our two situations. So we can draw some conclusions. The conclusions are that SPRT is a very consolidated decision approach and requires binary problems and independent identically distributed events. In this case, we could compare because we tackled a binary problem. And so we could compare the quantum inspired to the SPRT. QMC is a quantum inspired early decision approach, which is very tolerant to non-standardized numerical features and small training set, and this has been also demonstrated by the results, because with a split in 30-70 over 95% of accuracy is a very good result. And we have a lot of possible applications. This is prevention, predictive maintenance. We have been testing also in predictive maintenance and also in toxic leakage detections. So there are, and many others. There are new possible expansions of this method because we could apply new, we could test some theoretical developments with possible falsification for alpha, because alpha has been defined from theory as the square root, but if we transform alpha as f to the power of grade with grade in R plus, we can kind of falsify the theory, and we can see that from first early test that I've done on this, it's possible to demonstrate that you can get even further improvement with bringing the classification accuracy also up to 98%. Depending on the task, depending on many other problems, but it's a good possible expansion in future developments. One known issue that we have with QMC is the fact that memory in non-binary settings can be overloaded by the fact that we use the tensor product. And there are also new challenges that we can apply, we can tackle. We can try to apply the quantum-inspired approach to multi-objective optimization. Again, it's a possible future application. Thank you for your attention. It's over.